Hello everybody, my name is Robert Buchmann and I'm representing one of 7 universities involved in the proposal of this paper. All of us are members of an ecosystem and a collaborative network which is called OMiLAB, a community that advocates the value of conceptual models. My presentation will give you an overview of one of the key assets of this ecosystem, the smart innovation environment that was designed by the core team of OMiLAB in response to what we consider to be an education design problem. So the problem statement is formulated here through a design science lens as follows. We tackle an education design problem expressed by the question, how can we develop the digital engineer skill profile, considering that according to the literature, this implies several historically disconnected skills and technologies. The proposed treatment to this problem is a multi-layered innovation environment that can be adopted either as a didactic or a research experimentation lab. The term digital engineer is not new, however, it's been redefined recurrently. We are motivated by the definition displayed on this slide, which suggests a need to integrate physical and business operations with the help of digital technology, from Holland and Crompton 2013. So our goal is to foster this skill profile through an integrated experience, a so-called integrated separation of concerns across the 3 following views. A business view placing the focus on business idea development, a conceptual modeling view placing the focus on the value of models seen as semantically rich abstractions, and an engineering view placing the focus on digital twins and cyber-physical demonstrators. You may notice that we also included here the term digital innovator, which is a facet of this skill profile targeted for business schools and in particular business informatics programs. Since we took the path of design science in building the proposed environment, we started from some requirements collected from across projects developed by the OMiLAB network. They are briefly enumerated here as the technology requirement, meaning a requirement for fast prototyping platforms, the openness requirement, meaning a requirement for open platforms, open interfaces to facilitate artifact reuse, the digital integration requirement, which refers to a requirement for machine-readable bridging across those 3 views, which I remind you are business, conceptual, and engineering. The modeling method agility requirement, meaning that modeling tools should be available out of the box. However, there should also be a way to tailor them for domain-specific purposes. And finally, the knowledge ecosystem requirement, meaning that a platform should be set up for sharing and disseminating knowledge assets and learned lessons. This is an overview of the designed environment. As I said, it is an innovation environment aimed to support 3 phases of an innovation process: idea development, conceptual design, and proof of concept engineering. For each of these 3 phases, a separate workspace with adequate toolkits was designed and integrated. There is a digital design thinking workspace focusing on the business view. There is a conceptual modeling workspace focusing on conceptualization and smart designs, and the digital experimentation workspace focusing on execution and demonstration. The logos visible below are some suggestions of the technological ingredients included in those toolkits. Next, I will go into some details about those ingredients and about the scope of each particular workspace. The first one is called the digital design thinking workspace. We all know what design thinking is in general. It's a solution development approach that is characterized by being human-centric, participatory, and iterative. It is commonly employed as a workshop format by business analysts or requirements engineers, and the typical artifacts that are employed during those workshops are color-coded post-its and tactile storyboards with paper figurines. Our environment provides one specific workspace where design thinking workshops are supported with digitization tools. For example, the Scene2Model tool imports paper storyboards into digital diagrams to be further mapped on process maps or business process models. This is done with the help of a webcam and an ontology of concepts which are mapped on the popular figurine set, which is known under the name of SAP Scenes. The second workspace has two key assets. On one hand, out-of-the-box modeling support is provided in the BIAP tool, where the business ideas developed in the first workspace can be refined and translated here into conceptual models. On the other hand, a framework for tailoring modeling tools for domain-specific purposes is provided. This framework is called Agile Modeling Method Engineering, or in short, AME. Together, the modeling tool and the framework for adapting it ensure an open-ended semantic space for the conceptual models that are created in this workspace. Here are some details on the BIAP modeling tool. It supports multiple languages to capture different granularities, different abstractions. For example, it supports BPMN, UML, DMN, EPC, ER, PetriNets, and others. It provides some semantic integration between concepts of these languages, and it also provides some interoperability features that can connect the model contents to external environments. Some examples are HTTP requests that can be triggered by model elements. Diagrams can be exported as RDF graphs regardless of the diagram type. A web service mode can expose model contents to external apps. In addition to that modeling toolkit, the workspace also provides a meta-modeling framework, AME, as I mentioned earlier, that can be employed to tailor the modeling tool for various domains and purposes. This picture suggests the meta-modeling approach where custom modeling tools can be implemented by manipulating their meta-model layer. The main platform employed for this purpose is AdoXX, which has a free version at the provided link. Here is a classification of typical adaptations that can be made with the help of this framework. There can be adaptations in notation, meaning to align some graphical symbols with a business context. There can be adaptations in syntax, which means to add new verifiable syntactic constraints. There can be adaptations in semantics, which means to add new concepts or even entirely new model types to the language. And finally, adaptations in functionality, which refers to new features added to the modeling tool or interoperability mechanisms for new external model-driven systems. Of course, there are propagations between these categories. Change requests will typically propagate from one category to another, and these propagations must be traced with dedicated tools and dedicated management approaches. From a methodological viewpoint, AME is an iterative process comprising the following phases. The first phase is called Create. This is where we collect requirements and domain knowledge. Often this step will take input from the business scenarios identified during the design thinking workshops and in that workspace. The second phase is called Design. This is where we redesign the modeling method components from graphical symbols to semantics and functional features. The third step is called Formalize, which is a scientific step often skipped in purely didactic projects. The fourth step is called Develop, where the modeling tool is adapted through a meta-modeling approach. And finally, the step called Deploy, where the new modeling tool becomes available to expose enriched model contents to the next workspace, the one that focuses on digital engineering. Finally, the third workspace provides technological support for creating and experimenting with demonstrators, either virtual or physical ones. On a software level, a web integration platform called OLive provides numerous interoperability connectors, and on a hardware level, a starter package of robotic and IoT devices is provided, including adapters based on Raspberry Pis or a robotic operating system. What we see here are some exemplary demonstrators that have been built in this workspace. On the left side, we can see a video capture of the physical proof of concept, whereas on the right side, we see so-called smart models, in the sense that they are not traditional diagrams, but rather models that are semantically rich, interactive, and even interoperable. First, what we see here is a smart logistics demo driven by domain-specific language, and here we see a robotic arm that obeys the movement rules expressed as a PetriNet model. And now my presentation comes to a conclusion that the treatment to the education design problem that I mentioned in the beginning is this experimentation environment that integrates with a knowledge-driven approach 3 abstraction layers: a business layer for innovation co-creation, a smart modeling layer acting as a semantic bridge between the business ideas and the cyber-physical experiments, and the digital experimentation layer where cyber-physical proofs of concept are engineered. Experimentation and teaching can be confined to a single layer of these. However, taken together, the 3 layers can reconnect the so-called historically disconnected skills in order to support a full design research cycle from the design problem formulation down to the artifact engineering. This is a photograph from one such innovation environment, which is instantiated at universities, typically under the label of Innovation Corner. And this is a summer school where projects developed within this environment have been disseminated, this being related to the knowledge ecosystem requirement that I mentioned in the beginning. Several workshops and publications, some of them attached to well-known conferences, are also part of the dissemination ecosystem. For example, this book collects examples of modeling methods that have been developed over the years by the OMiLAB community. Thank you. If you have any questions, feel free to contact us. This is Professor Karagiannis, the initiator of the OMiLAB ecosystem, and my name is Robert Buchmann. I'm representing Babeș Bolyai University, and I'm also personally involved in contributing to this ecosystem. Thank you again.